far we've focused solely on the global structure of the distribution, the fact that you can take it and factorize it as a product of factors that correspond to subsets of variables. But it turns out that you also have other types of structures that you might want to encode, and that is actually really important for real-world applications. So to motivate that, let's look at the tabular representation of conditional probability distributions, which is what we've used universally until now in the examples that we've given. So a tabular representation is one of these examples where we have, a row for each assignment. So this is just a reminder, this is G with parents I and V. And here we have a row for each assignment of the parents that gives us explicitly enumerating all of the entries that correspond to the probabilities of the variable G. So this is great, and you can say, well, what's the problem? I mean, it sounds like a perfectly reasonable and very understandable representation. Well, that's great, but now let's consider a more realistic example, for instance, in a medical application where we might have a variable corresponding to cough. Well, there's lots and lots of things that might make you cough. You might have pneumonia, or the flu, or tuberculosis, or bronchitis, or just a common cold. And by the time you finish enumerating all of the many things that might make you cough, you realize that the variable usually might have as many as 10 or 15 or even 20 parents for a variable such as fever. So when you think about what the implications of that are relative to a tabular CPD, you realize that if we have k parents, and let's assume for the moment that they're all binary just for simplicity, then the number of entries in the CPD grows as 2 to the k, or O of 2 to the k, depending on the number of variable values of the child. So unfortunately, these situations are more common than not. And that means that tabular representations are really not suitable for a lot of real-world applications. So we have to think beyond that. So fortunately, there's nothing in the definition of a Bayesian network that imposes on us a fully specified table as the only representation of a conditional probability distribution. The only thing we need is that the CPD P of x given y1 up to yk needs to specify a distribution over x for each assignment y1 to yk. And it can do that completely implicitly. It can do that as a little piece of C code that looks at y1 up to yk and prints out a distribution over x. Now, fortunately, we don't usually have or in fact, we can use any function, parameterized or as a C routine or anything, to specify a factor over the scope x, y1 up to yk, such that, well, it has to be a probability distribution over x, so it has to sum. So when you sum up all the values of x for a given assignment to y1 up to yk, it has to sum to 1. Anything that satisfies these criteria, these constraints, is a legitimate representation of a CPD. So, like I said, fortunately, we don't usually have to resort to C code to specify CPDs. The framework of statistics has defined for us a multitude of different representations of a conditional probability distribution given a set of conditioning variables. So some examples include deterministic CPDs, where x is a deterministic function of y1 up to yk. We've already seen a couple of examples of that. We can define, and we will define, CPDs that have the form of what's called a decision tree or regression tree, a framework that some of you have seen before. You can think of CPDs that are logistic functions or more generally log linear models. We're going to talk about things that are noisy or, noisy and, which are noisy versions of deterministic CPDs. And then in the continuous case, we also have frameworks that allow us to represent the probability distribution of a continuous variable on a set of continuous or discrete parents. And that is really critical because obviously when you have a variable that takes on a continuum of values, you can't possibly write down a table that lists every single one of them. Now, one of the things that are intertwined with the notion of structure within a CPD is a useful notion called context-specific independence. And it turns out that this notion arises in some of the representations of CPDs that we're going to talk about. Context-specific independence is a type of independence that is where we have a set of variables x, a set of variables y, a set of variables z, and then we have a particular assignment c, which is an assignment to some set of variables, big C. So this is conditioning. This is an independent statement that only holds for particular values of the conditioning variable C, as opposed to all values of the conditioning variable C. Now, the definition of this is exactly as we have seen before, so except that if you remember before we had Z stays, when we were doing conditional independence given Z, we had the Z stays on the right-hand side of the conditioning bar everywhere. Well, now Z and C stay on the right-hand side of the conditioning bar in all of these forms of the independent statement. So let's look at why context-specific independence might arise when we have particular internal structure within a CPD. So let's imagine, let's consider the case that X is a deterministic OR of Y1 and Y2. And the question is, what form of context-specific independence holds when we have X being a deterministic, X being this deterministic OR? Okay, so let's look at these statements one at a time. And here we have that Y2 is false. And when what happens when Y2 is false? Well, when Y2 is false, X is the same as Y1, in which case, obviously, they're not going to be independent. On the other hand, what if Y2 is true? Y2 is true, I don't care about Y1 anymore, because if Y2 is true, X is true. And so here we have a notion of context-specific independence. What about this one? I'm now asking about Y1 being independent of Y2 given two possible values of X. What happens when X is false? What do I know about Y1 and Y2? They're both false. Well, if they're both false, then they're independent of each other. Because if you tell me that one of them is false, I already know the other one's false, so they're independent. And so this is another context-specific independence that holds here. Does it hold if I tell you that X is true? No, because I don't know which of Y1 and Y2 made X true. And so this last one doesn't hold. And so here are two context-specific independencies that hold in the context of deterministic CPD that wouldn't hold, neither of these would hold for general purpose CPD, wouldn't necessarily hold for general purpose CPD, where of X depending on Y1 and Y2.